And yeah, looks like we're back.
Cool. Yeah, and Ben, you'll be muted when you come back, so you can unmute and just check your mic if you want to.
Yeah, awesome. I think it works, right?
Great. Yep, perfect.
Great.
All right, well, we'll give it another 30 seconds or so. People are beginning to trickle in more quickly now. And then I'll let you know when we'll get started. When I start doing the introductory stuff, Ben, you can feel free to go ahead and share your slides. I'll stop sharing before I do my introduction.
And Krista said she's in lab, so we're recording this, right?
Yes. Oh, yes.
Okay.
Yes, we're recording it. That's worked out amazingly reliably since we started doing this last August.
Good deal.
Yeah, good deal. Can't complain. All right, since people know that I tend to do some announcements at the beginning of this, they're probably waiting 2 minutes for me to shut up so they can come in. So I'm going to stop sharing. They've gotten wise to my scheme, and let's go ahead and get going. So welcome back, everybody, to the SMU Physics Department Speaker Series for Spring 2021. We are continuing today our February series and its theme of Probing the Unknown. And in a moment, I'll hand things over to Professor Fred Olmos to introduce our speaker, Dr. Ben Nachman. But before we get to that point, I just wanted to make some announcements here. So the first announcement is that there's actually a special SMU Atlas seminar tomorrow at 11 a.m. Of course, everyone in physics is welcome to join in if they can, if they don't have other conflicts. The topic is available from the department seminar page, so you can go check that out if you want to see what it is. And if you might be interested in joining in, please contact Professors Allison Dayana or Jingbo Yi for connection information. They have all the Zoom-related organizational details. And then finally, a reminder to our audience on Zoom that we've got everything muted to avoid the hot mic problem because we're recording and streaming. So to ask a question on Zoom, where it's an interactive meeting, just type the word "speak" in the chat window, and at the next opportunity, slide change, or if it's during the Q&A session after the previous person has asked their questions, we'll get you unmuted and you can go ahead and ask your question or make your comment. So I'll be acting as just a mic and chat monitor for all that stuff during the event. And this event is being recorded on Zoom and simultaneously live streamed and recorded on YouTube. So hello to our viewers on YouTube. We always have something like 2 to 8 viewers on YouTube during the course of the event. All right, finally, let me welcome Professor Fred Olmos to introduce today's speaker. Take it away, Fred.
Very good. Yeah, it's a great pleasure to, great pleasure to have Benjamin Nachman with us today. He did his undergraduate at Cornell and then was a Churchill Scholar at Cambridge, where he got his MS, and did his PhD at Stanford, and then moved on as a Chamberlain Fellow at Berkeley from there, and is now a staff scientist at Berkeley. And he's leading a new cross-cutting group in machine learning for fundamental physics. He's also a member of Atlas collaboration at CERN, and he was the 2008 Wiki Tung Award winner from the CTEC collaboration for significant contributions to experimental studies of jet substructure. And just last week on the archive, he and our former grad student, Matthew Fiker, put out a preprint, a living review of machine learning for particle physics. And you can download the paper. It's got a link to the GitHub. And the idea is to keep it updated to get all the latest news on machine learning. And I understand he has a rather unique thesis, so I'll turn it back to Professor Sekula to talk about that.
Yeah, I mean, I don't know how you feel about your PhD thesis, Ben, but it is an impressive piece of work. If I remember correctly, it's just over 1,000 pages long. Is that right, Ben?
Yes, that's right.
Yeah. And I have used it. I always tell my grad students, go take a look at this, but please don't feel I'm setting an unreasonable standard for you.
Thank you very much for the introduction and for the very fine compliments. Shall we begin?
Oh yes, please take it away, Ben. It's all yours.
Great, very good. Yeah, thank you very much for the invitation today. Sorry for the toggling around. It took me a second to get the screen sharing working. So today I will talk about high-dimensional jet measurements in PP and EP collisions, and you'll see where the connection to machine learning comes as the talk evolves. All right. Oops. So if I go, there we go. Okay, so the physics motivation for this talk today will be to study the strong force. And I probably don't have to tell all of you why the strong force is interesting, but The strong force, or as we know it as quantum chromodynamics, is very different than the other fundamental forces, has a lot of interesting and exciting features. It's inherently interesting and complex for a variety of reasons. And for instance, it has some mysteries, like why the proton looks, or the neutron looks more like the left bottom picture, not the right bottom picture. But it also may be a gateway to discovering new fundamental structure. Because, for instance, when we collide protons at the LHC or other colliders, that's our way of probing very small distance scales at very high energy. And inevitably, it will involve quarks and gluons to some extent. Okay. And whenever we talk about the strong force at very high energy, it will almost always involve jets. And so one of the features of the strong force is that we don't get to observe the fundamental participants of the strong force directly. We don't get to see quarks and gluons. Instead, we scatter quarks and gluons, and out comes jets. And jets are these collimated sprays of particles that result from high energy quarks and gluons that radiate and then form bound states and hit our detectors. And you can see this snapshot of a picture from the ATLAS experiment where the protons are incoming and the indicated with white arrows, and then out goes this spray of particles. And you can see the reconstructed trajectories of the charged particles as orange lines, and then the yellow and green blobs are localized energy deposits in our calorimeters. Now, these jets, as you might imagine, have a complex substructure, and we can use this substructure for a variety of studies of the strong force. Okay, now here is a schematic picture of sort of the same thing, not to scale, that shows the evolution of, say, a proton-proton collision all the way from the smallest distance scales, something like 10 to the minus 20 meters, all the way up to the physical length scales in our detector, reaching meter length scales. And this is a mess. So there's a lot of particles, but also it's a rich opportunity to explore the various features of the events to learn something about the underlying physics. And so here, sort of shown schematically, we have, in this case, 2 protons coming in. These are the 3 lines here and here, representing 3 quarks. Then they're sandwiched together, and the incoming quarks and gluons inside the protons collide. There's some high energy reaction that happens, and then out goes quarks and gluons. Those quarks and gluons, they radiate, they form hadrons that are these pancakes, which then decay, which are shown as arrows, and further radiate. And then the hadrons fly for some distance, hit our detector. They're reconstructed in various ways by registering detector signals, and then reconstructed as particle trajectories. And there are a variety of experiments that are using that are colliding hadrons. So there's the 4 main experiments: the Large Hadron Collider, ATLAS, CMS, LHCb, and ELISE. There are other colliders, for instance, RIC, so where there's STAR and Phoenix and its future upgrade S-Phoenix. And there are a variety of other past experiments, proton-proton, electron-proton experiments, like the Hera experiments, which collided electrons and protons, and then future electron-proton and proton-proton experiments like the EIC in the US, and potentially other colliders at CERN and elsewhere. Now, of course, it's also interesting to collide leptons. You can do interesting QC with them as well, but I'm going to focus today on the messier and therefore more complex proton-proton and electron-proton initial states. Okay, so with this picture in mind, the idea is we want to extract the most QCD we can from these collisions. And for that, we want to make highly differential measurements. So we want to examine these radiation patterns in their natural high dimensionality. And this will be possible in part because we have a lot of data. So at the LHC and at past and future colliders, we have an immense store of collision data. But we also have very fine detectors, which have very precise detectors, which have fine granularity and allow us to reconstruct with great precision particle trajectories, including their positions and momenta, and in some cases also the particle types. And so to state the goal succinctly, we want to say something about the differential cross-section of particle properties. So we want to know something about the spectra of the hadrons that, all the particles rather, that would have hit our detector. But instead, we're confronted with the measured detector signal. So on the right, we have these reconstructed trajectories, and we want to be able to go from the right to the left. That's, in a nutshell, what the measurement problem is. And then once we have the left, we can do all sorts of inference questions to learn all sorts of inference tasks to learn something about the underlying properties of QCD. Okay, so how is this usually done? The typical solution is that we make an observable. So an observable is just you take the phase space and you project it down to one or a small number of dimensions. And then we take that observable and bin it into a small number of bins, and we can make a histogram. And once we have the histogram, we can turn the problem basically into a linear algebra problem. We can represent the histogram as a vector, and you can imagine representing the migrations between the particle level and detector level as a matrix. And then the measurement problem boils down to doing some kind of matrix inversion. And for a lot of reasons, you don't want to invert the matrix directly, but you can do some kind of regularized matrix inversion, which is very effective. And just to be clear here, to get this left picture, which shows the sort of migrations between the true values and the measured values, we have to have some kind of simulation of the detector, which allows us to know the relationship between the particle level version of our observable and the detector level version of our observable. Okay, so that's great, but this has a sort of fundamental challenges. So one is that it's inherently binned, and the binning is fixed. So once you've set the binning at the beginning of your measurement, you're stuck with it until the end. And there's really no way of making different bins unless those bins are a coarser version of the bins you already have. And another key challenge is that this works really, works effectively when you have a small number of dimensions, but does not work well when you have many, many dimensions. And it's non-trivial to add more dimensions. Basically, it works well for like a fixed number of bins, and you can trade off the number of bins per dimension. So you could have many observables that are very coarse, or you could have one observable that's very fine. Okay, so can we go unbinned? Can we go in many dimensions? And that will be sort of the focus of this talk. And so I'm going to introduce an algorithm that is called Omnifold. And Omnifold is an unfolding algorithm, so it achieves this inversion from detector level to particle level. And I'm going to first introduce the algorithm, and then I'm going to show you how it can very naturally account for high-dimensional observables. And so roughly speaking, the idea is that there's like 4 data sets. There's on the one hand, the ones at detector level. So we observe some spectra on our detector that's measured. And then there's like the true particle level spectra. We don't get to observe that. That's what we want to infer. And then we're aided, and we want to go from black to green, basically. That's the arrow, as the arrow depicts. And we're aided in this task with a simulation. And the simulation has also those 2 features. So there's also like the detector level simulation, which I'm just going to call simulation. And there's the particle level version of that, which is we're going to call generation. And these little boxes are supposed to remind you of computers. These are like to show this is synthetic. And the idea is that on the synthetic side, we have a matching between the particle level and the detector level. So we know for a given event, the hadrons that hit our detector and the signals that they represented. And so that's going to allow us to basically invert this map from data to ideal. Okay, so let me introduce the idea. And it's an iterative algorithm. So there's going to be 2 steps that are repeated n times. And n is a hyperparameter. You'll have to optimize the exact value. Okay, so the first step basically is we take our simulation at detector level, and we reweight it. So we learn weights that basically make our simulation at detector level look as similar as possible to data. And for now, I'm not going to say where those weights come from. I'm just going to assume that I can do that. And then once I have my weighted simulation, any histograms or whatever observables you want to compute, they look the same between data and simulation. And I'll talk later about how we get this weighting function. Okay, so but then I can use the fact that in my synthetic environment, I have a matching between detector level and particle level. So for a given event, a given collision event, I have these weights I just derived at detector level. I can just literally inherit them at particle level. So the given particle level can just use the same weights. And then you might say, well, okay, why don't I just stop there? Now I'm done. I have a bunch of weights. I have my particle level simulation, and the detector level simulation matches the data as well as it can. Why is it not the end? And it's not the end because these weights that I've just pulled back to particle level, they're not a real function of the particle level phase space. Because the detector effects are not one-to-one, right? You could have one particle level phase space point be mapped to two detector level events. And if those two detector level events get different weights, then basically I'm going to have a problem where I have the same phase space point have different values. And that's not a proper function. A function, a function has to have the same value if I give it the same input. And so we have a second step. And the second step, you can think of as a regularization step. And the idea is that basically you learn a second reweighting to go between the unweighted particle level and the weighted particle level. And then that reweighting is, by construction, a proper function of the particle level phase space. And now I have, for every particle level point, I have a unique weight. And now you could say, okay, so now I'm happy. I have particle level simulation with a bunch of weights, and that should be very close to the ideal. And we could stop there, but we can also repeat the whole procedure. Once again, we can take advantage of the fact that we have this matching between particle level and detector level. And so the weights we just derived at particle level can be inherited at detector level. And then once again, I can use those weights to reweight between detector level simulation and the data. And then I can pull back the weights. I can train a second reweighting between the particle level and itself with the weights. I can push the weights forward, et cetera, et cetera. So you can repeat this procedure n times, where at every iteration, there are two steps. There's this reweighting at detector level and the reweighting at particle level. And then, so yeah, there's these two reweightings, and then we use the connection between particle level and detector level to inherit the weights between the different levels. So before I get into a real example with particle physics data or simulations, I want to give you some more intuition by walking through a toy example to see exactly what this algorithm does. The end here is that you have a particle level simulation with weights, and then you can do whatever you want with it as your estimate for the truth. Okay, so to give you an example, let's take a very simple case where I have literally only two possible values of my observable. I have two possible values at particle level and two possible values at detector level. And they're going to be called 1 and 2. Those are the two values. So it's like a histogram that's binned. And I advertised this in the beginning by saying that we can go unbinned. And so clearly we want to go unbinned, but for now to build intuition, we're just going to have binned, and there's only two values. And so on the left side, this is going to be the synthetic, and the right side is going to be the natural. And so in particular, we're going to use the measured, and we want to infer the ideal. And imagine that we have, on the synthetic side, we have some simulation, and the prior in the simulation is that the two values are equally likely at particle level. Right? So that's the generation. And further suppose that the detector effects have the following migration matrix. So the migrations are, if all of the ones in the first bin are reconstructed properly in the first bin, so there's no migrations, but the events in the second bin, they're evenly split between the two possibilities at detector level. And so if you apply this migration matrix to the particle level simulation, you get the following detector level effect. So basically, all of the ones stayed as ones, and then half of the twos became ones, and half the twos stayed as twos. And so then you can see basically what it looks like. So you have basically 2/3 in this first bin and 1/3 in the second bin. Okay, and so this is what it looks like. And now imagine that the detector level data looks like this. So it's 50-50. And so basically my predicted detector level is the pink, and my observed is the gray. So clearly my prior was wrong. My prior did not give the right answer. And so I need to update my prior. And that's the whole point of the Omnifold procedure. And so the first step of the Omnifold procedure is to derive weights based on the pink to match the gray. And so in this case, the weights are easy to derive. So basically I need to make the pink here twice as high. I need to make the pink here 2/3 as low. And then if I do that, then the pink will match the gray. Okay. And then I want to assign want to pull back those weights to the particle level, so to the blue. And now I have to remember where the pink came from, right? So all these pink ones came from 1, and these 2 darker pink ones came from 2. So basically all the ones here get a weight of 2/3, and all the ones here get a weight of 2. And so in particular, if I think of like all the 2s here, half the 2s were reconstructed as 1s, and half the 2s are reconstructed as 2s. So half the truth 2s get a weight of 2, and half the truth 2s get a weight of 2/3, while all the truth 1s get a weight of just 2/3. And if I apply those weights, then I get a new particle level distribution, and that's the new blue lines. So basically they were 50-50 before, and then after one step, I've upweighted the 2s and downweighted the 1s. And then I can then once again apply this response matrix to the blue to get what my new predicted detector level distribution would be. And this is what it looks like. So once again, half the 2s become 1s, and all the 1s stay as 1s. And so this is what it looks like. And so basically I can repeat the same procedure again. So I can say, okay, I want to match the pink to the gray. The gray hasn't changed. And so now I can see that in order to make the match, I have to multiply different factors than I did before. And so here, for instance, there's 1/3 of the pink is here, but I want it to be a half. So in order to make a third become a half, I multiply by 3/2. And there's 2/3 of the pink is here. In order to make the 2/3 become 1/2, I multiply by 3/4. And then once again, you can remember which one came from which one. And you repeat the procedure, and now you see it looks like this. So the blue in 2 became a little bit higher, and the blue for 1 became a little bit lower. Okay, and you can imagine repeating this procedure many, many times. And you'll find that if you repeat infinitely many times, it converges to the following, where it basically says all the generation, all the particle level events should be 2, and there should be none in 1. And if you think about it, you see that makes sense. If I put everything in 2, half will go to 1 and half will go to 2, and it works out. That in fact would reproduce the gray. So that's great. And it's worth noting that if you had actually, instead of doing this iterative procedure, if you had just applied probability of ideal given measured, you would actually get the wrong answer. And the answer that you get here is the maximum likelihood estimate. And so here is just an illustration of how the iterative process works. And now I want to show basically how this works in practice, not just in the bin case and not just for this toy example. Okay. And basically so far I've said almost nothing about reweighting. In the toy example, the reweighting was trivial because they're binned. I can just like literally measure what the fraction is and then divide by the fractions and get the target reweighting. But how am I going to do that without binning? And so the generic problem is that I have some data sampled from one distribution P of X and some data sampled from another distribution Q of X. And I want to create weights, which are basically the ratio of the two densities. So the ideal weight W would be Q of X over P of X. And if I have those weights, then when data set 1 is weighted by 2, it is statistically identical to data set 2, which is what I want. So then the question becomes, well, how do I do this if I don't know or can't know P and Q? And in all the interesting examples we have in collider physics, we're not going to be able to compute P and Q directly, in part because X is high dimensional. That's the whole point. And we don't have access to the probability density. We can make many calculations, but basically we can sample from the distribution of P and Q, but we cannot write down P and Q explicitly as densities, take the ratio. Okay. And the solution to this problem is going to be machine learning. And so this is where the deep learning comes in, and with a very simple but very important fact, which is that neural networks basically learn to approximate the likelihood ratio, Q over P. And there's some technical details. It turns out that the exact, what exactly they learn depends on how you set up the training. But there's a known relationship between how you set up the training and the likelihood ratio. So this is great. Basically, I can learn the likelihood ratio directly by training a classifier to distinguish two data sets, because it turns out that the optimal classifier is actually the likelihood ratio between the two densities. And so this is fantastic. I've turned the problem of density estimation, which is very hard, so that is to say, learning P and Q separately from the data and then taking the ratio, to the problem of classification, which is much easier. So instead of learning P and Q and taking the ratio, I simply can learn P over Q or Q over P directly. Okay, so now let me show you how this works in practice for data sets we care about for collider physics. And so I'm going to use as an example electron-proton scattering. And so, for example, think about electron-proton scattering at Hera, where the center of mass energy was something like 300 GeV, and you get pictures that look like this, where the center event display is a cross-section of the collider, and you can see a jet recoiling against the electron. And the sort of Feynman-like diagram is shown on the left for what we have in mind, where the electron exchanges a virtual photon with the proton components, and you get this quark that's knocked out and becomes a jet. And basically, you can use the jets to study nuclear structure, among other things. And the key observables here are related to the jet and electron properties, as well as other event properties, like, for instance, the momentum of the virtual photon, which is often called Q. Okay, and so, for instance, let's imagine we want to examine the distribution of Q squared, which is related to the, this momentum of the exchange virtual photon. So neural networks are really great for this reweighting because they're naturally unbinned and they can readily process high-dimensional data. So when you're training a neural network, like the one that's shown in the bottom right, just schematically, it's trivial to add more features. So adding another dimension just means literally adding another node, which technically means changing like, a 2 to a 3 in a line of Python, which is incredibly easy. And then for this particular example, it's being shown here. So this is the histogram of the log Q squared distribution, and in simulation with different simulators. So there's a simulator called Django, and there's a simulation called RapGap. It doesn't really matter the details of these simulations, but they're both simulations of electron-proton collisions. And the point is that I want to reweight the purple to the green. And so we've trained a neural network to distinguish the purple and the green. And then we can interpret the output as a likelihood ratio and then apply it as weights to the purple. And if we do that, we get the black. And the point is that black looks just like the green. So you can see very precisely that this reweighting has been very effective. Now it's shown here as a binned histogram, but actually underlying this, there's an unbinned function. So there's a function, the reweighting function doesn't know at all about the binning. And so we could easily change the binning later as we like. It's just shown here for illustration. And so the reweighting is naturally unbinned. But we're not just interested in reweighting. Of course, there are many interesting applications that you can use for reweighting itself. We really want to do unfolding. We want to correct for detector effects. And so we want to be able to do that in high dimensions. And so here is just to say that so this was just one observable, but in fact, as I mentioned, it's like very simple to add more observables. So here are 8 observables now related to deep inelastic scattering observables, which have been simultaneously weighted from the purple to the green, and that's the black. So from Django to RapGap, and then the reweighted one is the black histogram. And so there's some jet kinematic properties. So like the top right is the jet pseudorapidity, which is related to the angle, the polar angle that the jet has in the detector. There's the transverse momentum, which is the middle top. Then there's the Q squared I already told you about. There's the elasticity, and there's a bunch of other properties like the electron jet angular spread. You can see they're mostly back to back. The jet phi, the jet azimuthal angle, the electron transverse momentum, and then the momentum balance between the jet and the electron, which is sometimes called QT. And in any case, you can see that the black and the green match very well everywhere here. So this is an 8-dimensional reweighting, and I'm only showing you the 8 dimensions, but actually it's the 8 one-dimensional projections. But if you looked at this space in 8 dimensions, which I definitely cannot look at a space in 8 dimensions, but if you have the ability to examine a space in 8 dimensions, you would see that every projection also is reweighted properly as well. So it's really precise and high-dimensional reweighting. Okay. So now I want to iterate this reweighting in 8 dimensions in order to perform the unfolding. So just as a reminder, we have the simulation on the bottom and we have the data on the top. And we want to go from the top left to the top right using this iterative reweighting procedure. Okay, and so here's the same 8 observables I showed you before with the jet and electron properties. And it's the same kind of closure test where we're going to call basically Django is like the data and RapGap will be like the simulation. And so we're going to use one to unfold the other. And if it works properly, we expect that when we unfold Django with RapGap, we should get the Django truth. And in fact, that's what we see. So here we've repeated this Omnifold procedure some number of times. And we have this 8-dimensional phase space. And you can see that the black and the orange match very well. And across a wide variety of observables and also over a large and dynamic range in the cross-section, which you can see very nicely, for instance, in the bottom right, you can see that there's a non-trivial difference between the two simulators. So the prior is different than the target, but the iterative unfolding procedure, which is done maximum likelihood, has basically removed the prior dependence, which is exactly what we want. Okay. So now just to highlight or to recap some of the properties of Omnifold. So it's naturally unbinned. Not only is it unbinned, it's also high dimensional. So it's 8-dimensional here. And one of the nice features about being 8-dimensional is that you can pick any combination of observables. And then after the fact, you also have that is also unfolded. So the whole 8-dimensional space is unfolded. And so any observable on the 8-dimensional space is itself also unfolded. The advantage of being unbinned is that it's very easy to rebin later. So let's say you want to compare to a theory calculation, or you want to compare to another experimental result. It's a very big challenge to recast or to compare, often because the binning is fixed and it's non-ideal. And so you'd like to rebin later, and this makes it very easy to do so. It's also maximum likelihood. I haven't proved this to you, but in fact, one can show that the Omnifold procedure, this iterative procedure, actually converges to the maximum likelihood estimate, which has some nice statistical properties. And furthermore, actually the Omnifold procedure converges to a method that is quite common in collider physics and is widely used, called iterative Bayesian unfolding. And the name Bayesian is a bit of a misnomer. It's basically a repeated application of this reweighting scheme that I told you about. And then one last thing, which is also a side benefit of Omnifold, is that by including more features, you can improve the resolution from correlations with the detector response. So basically, if you think about the binned version, if your response matrix, if the matrix you're trying to invert is diagonal, so as I say, like, if you start in some particular bin and you end up in the same bin, then the unfolding is trivial. You don't do anything. And so if the resolution of some observable depends on another observable that you're including in the unfolding, then your response matrix effectively becomes more diagonal. And for these particular observables, for instance, a lot of the resolution is dictated by, for instance, where you are in the detector and the energy scale of the objects. And so because we include the kinematics of the objects that we're measuring, we basically get for free all the dependencies of the resolution on those kinematic properties. Okay. But now in the basically last part of this talk, I want to mention another interesting possibility, which is that so far I've talked about observables that are still relatively high level. So in the deep elastic scattering, talking about the electron and jet properties. But of course, there's a lot more complexity in these collisions. We have all of the hadrons that are produced from the scattering. And so you could imagine another possibility, which is that you actually apply Omnifold directly on the lowest level inputs that you have available. For instance, energy flow particles, which are like candidates for individual hadrons produced in the collision. And if you unfolded that phase space, which we'll call the full phase space, then you can construct any observable after the measurement. So that would be a qualitatively different way of doing measurements, where instead of specifying the observable ahead of time, you unfold everything, and then later you specify the observable. So what I've already showed you is quite different than before, because the binding is no longer specified ahead of time. But what I'm now saying is that you could even specify the observable later. So let me show you how that would work. For that, I'm going to use another example, and the example is going to be a particular event, type of event at the LHC. So let's consider the production of a Z boson produced in association with hadrons. So here's an event display from the Atlas experiment, where you're kind of looking at it from the side. So the protons are coming sort of diagonally into and out of the page, and these red lines represent muons. So the Z boson can be reconstructed very precisely because of its decay to muons. And then you see all this other, all the other particles that are produced in the event. The orange lines are reconstructed charged particle trajectories, and then the yellow and green blobs are deposits in our calorimeters. And those will represent the other hadrons that we want to learn something about. And these kind of events are nice because the Z can be used to very precisely measure these events, very precisely isolate these events. Then we can basically measure the hadronic recoil. And a challenge about these events is that they have a variable number of particles. So you might have anywhere from tens to hundreds of particles. And due to quantum mechanics, there's no particular order. So they have a symmetry, which is that they're permutation invariant. And so it would be great if we could apply the reweighting technology that I just told you about on data sets for which it's inherently equipped with those symmetries. And in fact, there is a neural network architecture that's called deep sets. And the deep sets architecture basically is a neural network that acts on variable length sets. And I'm going to tell you about it in a second. And there's a high energy physics version of deep sets that's called particle flow networks. And so I'm going to show you how we can use particle flow networks to implement Omnifold on the full phase space. Okay, so the way that this deep sets technology works is that we have a variable number of particles, and each particle has some features. So they at least have the 4 vector of the particles, but maybe other features like charge or other electric charge or other properties. And the way it works is that you learn 2 neural networks. One neural network is this little one shown here, which is an embedding network. So basically you take each particle and you embed it into some latent space. And latent space just means some abstract space that has a fixed dimension. And the dimension of the latent space is a hyperparameter that we have to optimize. And then we apply that neural network, the embedding neural network, to every particle. And the input to this embedding neural network are whatever the properties of the particles are. So they're 4 vectors and whatever other properties like electric charge. And then I have a list of vectors in a latent space, one for every particle that I am trying to learn something about. And that's where the permutation invariant step comes. So then I literally just sum over all these vectors in the latent space. And the summing has 2 important features. One, summing is naturally permutation invariant. And the other thing that's very important about the sum is that it's easy to add more particles. So if I have an event that has more particles, it's fine. I just run the sum over more vectors from the latent space. But after the sum step, I have a fixed vector in the latent space. And then I can apply sort of standard fixed neural network on that vector to produce my classifier output. And so these 2 components, the embedding neural network and then the sort of normal neural network that are composed together to get deep sets, and they're trained at the same time. So I'm going to not talk about any of the technical details of how that works. I'm happy to talk about it later. But basically, if you run this procedure, then it works. So on the full phase space, say in simulated proton-proton collisions, we find that basically you can achieve this reweighting when you compute any observable later. So here are 2 histograms which show some random observables. So the left is the number of particles in these collisions, and the right is some particle correlation, energy correlation function. And the point is that we're going from data set 1 to data set 2. And if I apply the weights to data set 1, then you see that the orange histogram matches the black dashed. And just keep in mind here that the function that we're learning is on the full phase space. So it acts on the level of particles, and then we're later computing these observables, and basically it matches. That's pretty amazing because these are just some random 1D observables, and of course we've checked many of them, and they all seem to match very precisely. And then just one kind of technical slide. This works really well even when the differences between the two samples are very small or very localized. And so here's a table of ratio plots basically between histograms. And each row represents different observables. So the first row is the number of particles in the event. The second row represents sort of the number of prongs that there are, number of hard prongs in the event, which you can think of as like the number of jets. The third row is this energy correlation, and the last row is the number of kaons in the event. So kaons are a type of hadron which contains a strange quark. And then the two columns represent basically different simulation variations. So in the left column, we've taken the simulation, we made a very, very small modification to the fragmentation. So how quarks become hadrons. This thing called A Lund is a parameter in the simulation package called Pythia. And by changing this parameter, it basically changes the whole phase space, but by a tiny bit. And the point is that the ratio between the original and the target distribution is in blue. And you see it has like a slope, and the size of the effect is roughly 10–20%. But after applying this full phase space reweighting, it becomes the orange. And the orange is consistent with unity everywhere. So it's basically learned all these very subtle differences in the phase space and corrected for them. And in the right column, we've changed only one parameter. And this time the parameter is how often basically you produce kaons. And so it should basically change nothing at all except for the number of kaons. And so like the top three ratio plots, you see the orange and the blue are the same. But the last one, you can see a huge effect where the number of kaons changed quite a bit. So the blue has like a order 1 effect basically. But the neural network has learned to basically ignore everything except for the number of kaons. And it just zoomed right in on that and reweighted that and kept everything else the same. These are just two examples where this high-dimensional full phase space reweighting has learned to very effectively and precisely identify small and distributed effects in the phase space. Okay, so now let me show you how we can apply this iterative unfolding methodology to the full phase space. And so as a reminder, once again, we're going to have detector level simulation, but it'll be like our data. And then we have a second simulation, which will act as our, which will have particle level and detector level simulation. But now the difference is that from the electron-proton example I gave you earlier is that we have the full phase space. So the data represented as a collection of particles that have 4 vectors and particle identification, so like charge and type, as opposed to just a small number of high-level observables. And so here's one picture for an observable. So in this case, this is like the mass of the leading jet in these Z plus jets events. And there are multiple lines here, so let me walk you through it. So there are the four data sets that I had mentioned at the beginning. So we have our data and our truth. The truth is the target, that's what we want to learn about. And then they're in quotations here because everything is simulation, and we just use a different simulation for the black and green than for the other ones. And then we have our synthetic, which is a different simulation. And we have, of course, the particle level simulation and the detector level simulation. And if you look, you see that the blue and the green are not the same, which is to say that our prior is not exactly correct, which is, it happens. Our simulations are only an approximation to nature. And so it's not uncommon that the simulations aren't exactly correct. And that's the whole reason we want our methods to be prior independent. And so we can apply Omnifold, and Omnifold goes from the data and tries to be a close approximation to the green. And so that's in red. And you see the red is pretty close to the green. And you can look at the ratio plot. The ratio plot is helpful to see. You want to be close to 1 as possible. And to compare, we have IBU. So IBU is this iterative Bayesian unfolding. This is a standard one-dimensional binned unfolding method that is widely used in collider physics. And you see that the gray also is pretty close to the green, but the red is closer. And the gray here is binned. So the red can be rebinned later if you like, but the gray, the binning you see is what you get. You can make it coarser, but not finer. And one of the reasons that the red is closer to the green is because the red here is a full phase-space unfolding. Actually, it doesn't know about jet mass. It just we unfold all the particles and then we compute the jet mass later. And so anything that affects the resolution of the jet mass is automatically included in the unfolding procedure. And in fact, one of the amazing things about Omnifold is that you don't have to stop with one observable. You can recycle the unfolding to compute any observables you like. And so here there are 6 observables. And I'm not going to spend time focusing on each one of these histograms, but basically there are a wide variety of observables that are related to the properties of the jet in the Z plus jet event. So there's the jet mass in the top left. There's the number of particles inside the jet in the top middle. And then there are a variety of other observables that characterize the radiation pattern, basically how spread out it is and various other aspects of the radiation pattern. And if you stare at all the ratio plots, you'll see that the red is basically everywhere closer to unity than the gray. And the gray is a per observable unfolding. So basically we have to repeat iterative Bayesian unfolding for every one of the 6 histograms, whereas the red is just one all at once. So not only is the red everywhere better than the gray, it's also requires less, fewer steps. Okay, and so this basically is going to bring me close to the end. And so this property of Omnifold, I think, will significantly increase the utility and future proofing of these data. So because if we can do sort of a full phase-space unfolding like this, of course we can change the binning later, but we can also change the observable later. So if we learn with new theoretical or experimental insight that certain observables or certain ways of representing various observables is more effective, then it's very easy to basically recast. It's basically trivial to recast old measurements, whereas much harder before. And thinking about future experiments like the Electron Ion Collider at Brookhaven and other future experiments, it's important to start thinking now about the challenges that we need if this paradigm is going to be the new one. In particular, how to represent and store unbinned measurements. So the data are no longer representable as a histogram or a vector. And so it's you need to think about how we actually do that. And also in terms of the machine learning itself. So I basically didn't talk about the machine learning, but of course need to ensure that you can load all the data into memory. So when you do matrix inversion, you just need to be able to read in the matrix, which is has n by n floats. That's it. Whereas if you do the full phase-space unfolding, you need to read in every event, and each event can have complex properties, and so therefore you might run into memory problems, and may need to lead to some interesting data parallel challenges when it comes to computing. Okay, so that's basically the end. And so I think by using deep learning and the Omnifold method, we're able to simultaneously unfold multiple unbinned spectra. And I think this will provide a wealth of information for probing QCD, as well as other effects, but in particular QCD in great detail, because we now have access to the full phase space and the complex radiation pattern that we can observe with proton-proton, electron-proton data. Now, the methodology here is general. It can be applied to any measurements, both in low and in high dimensions. All right, thank you very much for your time.
Okay, yeah, no, thank you very much, Ben. Let's go ahead and see if we can give you a little bit of applause here. I've got, there we go. Okay. All right, so I see we have a question from Pavel. So again, if people want to ask questions, just go ahead and type speak in the chat window and we'll get you in the queue. Go ahead, Pavel, you should be able to unmute.
Yes, hi, Ben. Well, thank you so much. These are all very interesting and important ideas. I wanted to ask you, what is known about mathematical properties of these algorithms? For example, well, clearly they are very complex and clearly you get some solution. But how do we know that this converged solution is really the truth? And how do we know that the truth is unique? So, well, and how also the other aspect is that how do we know that we really fit the truth and not the noise around the truth?
All excellent questions. So there's sort of two answers. The first answer is the formal answer. So if the neural networks are behaving as they should, so if they properly learn the likelihood ratio, then we can prove, and I don't want to get to the technical details, but we can prove that this procedure converges to the maximum likelihood estimate. So even in the full unbinned high-dimensional space, the result that you get is the maximum likelihood estimate, which has all sorts of nice statistical properties. So that's the one answer, which is maybe the simpler answer to state. Now there's the harder answer to state, which is that what if the neural networks aren't doing their job? And so there, you have sort of less guarantees about exactly what's going on, but there are of course a variety of handles to sort of quantify the uncertainties. And so there are a variety of types of uncertainties. And so some uncertainties related to statistical noise, and those you have, so the statistical fluctuations in the input data set, and those you have no matter what, whether it's neural network based or not. And so there you can estimate them in the usual way with like bootstrapping or whatever your favorite resampling technique is. The more nefarious problem is if the neural network does not estimate the likelihood ratio because of some limited expressivity. So say like you didn't train long enough, you didn't have enough nodes in your neural network, you didn't train with the right optimizer. And in that case, for the unfolding problem, one of the ways to diagnose this is basically in the usual non-closure checks. So I showed all of these checks. Let me go back to here. So basically we have two different simulators, we unfold one with the other. And if the neural network wasn't doing what it was supposed to be doing, you wouldn't see closure. And so that's like the usual problem. And even with matrix inversion, right, you do this kind of closure check, and you can use this to validate and sort of bound the size of the uncertainty from the fact that the neural network is not doing exactly what it's supposed to be doing.
Mm-hmm. But then how do you separate the signal from the truth, from the noise? Because clearly your real data will also have all sorts of kind of secondary effects. And is it again, is it controllable? Or is it do you really basically prevent the neural network from overfitting the data? And
right. So overfitting, underfitting. By now there are a lot of tricks for making that happen with regularization. So I'm not super worried about, and you can diagnose that once again with these closure checks. Now, the one fundamental assumption, though, is that the detector model is correct. And so if the detector model is not correct, then you'll get the wrong answer. And that's of course, a baseline assumption you have when you do normal unfolding. Even when you do matrix inversion, right? The matrix you assume is correct. And so here there's no matrix, it's more complicated. You have to assume it's correct. And of course, we have uncertainties on the simulation. Those will all feed into the setup, but that's a really important and critical assumption.
Okay. Okay, thank you so much. Mm-hmm.
Okay, and next up we have Tim Hobbs. Okay, Tim, you should be able to unmute. Go ahead.
Yeah, thanks, Steve. And thanks, Ben, for the really nice talk. I had just sort of a general question for you. So you gave a very nice demonstration of this unfolding technology for deeply inelastic scattering. You mentioned the EIC. I just thought I'd comment, as you know very well, many of our experimental colleagues are involved in detector development for the EIC. And generally, of course, this assumes some sort of binning scheme and so forth, perhaps inspired by Hera. I was wondering if you had any general comments about how these kinds of unfolding techniques, as you described, which move beyond specific, bin-dependent analyses, might really inform the detector development. And I would like to ask, is that being actually fed into the detector development now for the EIC, in your opinion?
Yeah, so I myself am just starting to get in, thinking about these kind of questions, but I think that it is an interesting time to think about sort of co-designing the analysis that you would do later with the detector design that you would want to have now. And in particular, the ultimate analysis would be like unfolding the full phase space. So here I showed, like in the Hera example, this is an 8-dimensional phase space, which is already pretty great. It's way bigger than the usual phase spaces people measure, but it's not the full phase space. Whereas in the Z plus jet example, this is really the full phase space. So like once we've done this measurement, like any observable you can think of that can be computed from the hadrons and Z plus jets can be measured later. And so to do this, you'd want to have so the equivalent of energy flow objects, which requires having both having good calorimetry combined with tracking capabilities, and a scheme for having uncertainties on all those objects, which is non-trivial. And I think that it would be interesting to think about the connection between the detector design,
Right.
and yeah, what's possible. And I haven't thought through it deeply, and I'd be very interested to talk more about it.
Okay, very good. Thank you so much, Ben.
All right, I don't see any other questions, but Ben, I was going to follow up on something that Pavel asked about, because it's still, some things are still bothering me about the realities of data and what that might do to upset the scale here. So for example, there are some things that we can't map back to in simulation. A good example in the LHC is pile up, either out of time or in time pile up, right? So you wind up with deposits of particles and energy in your detector that then you can't, there is no Pythia record of that stuff happening, right? It's simply not present. It's just put in the detector. It creates a noise map event by event in your detector system. And so at the end of it, you're going to get a bunch of observables like this, but they're going to have a contribution. Let's assume even that you only produce a signal ever in the simulation. You're still going to have a bunch of stuff overlaid on the signal for which you have no fundamental mapping back to the thing that caused it. How does Omnifold handle that kind of thing that can wash out observables like energy resolution or something like that? Yeah,
so there's a couple of points, and maybe I'll answer various questions. I'm not sure exactly which question you're asking, but let me answer a couple of questions. You can tell me if I hit it.
I'm not sure which question I'm asking either, so that will be helpful then.
Great. So first of all, resolution effects, no problem. If it's in the simulation, we correct for it. So that's good. So smearing is fine as long as your detector model is correct.
Okay. In other words, as long as you're smearing correctly the way nature intended you to.
Yeah, if you're if your energy resolution is exactly in your simulation is the same one that you have in data, great. You'll correct properly. Now, pileup is not exactly in the category. So they're kind of different kinds of. So pileup is made by particles, and the particles are also in the simulation. So it's not exactly a problem. But let me answer a related question, which is like, what about like noise, like genuine noise, like things that are not at particle level? And so unfolding actually doesn't just correct for like detector distortions. It also corrects for what sometimes people call like acceptance and efficiency effects. So like you have some particles produced that don't make detector signals, and you have some detector signals that didn't come from particles. And these are corrected for, so the unfolding, I didn't talk about it, it's a technical detail, but you can actually also correct for those in the unfolding. And the way it works is basically you can assign kind of empty symbols at one of the two levels, at particle level or detector level, and then the unfolding just sort of naturally removes them in the proper amount. And in fact, you can also do background subtraction. So let's say you want to measure like, I don't know, top quark pair production, but you want to remove the contribution from, let's say, W plus jet production. And so in a binned unfolding, what you would do is you would like measure the histogram of the T bar, measure the histogram of the W plus jet, subtract the histograms, do the matrix inversion.
Right.
So there is an unbinned version of that where you basically just take your W plus jet simulation, assign all of them a weight of -1, and then that is the unbinned version of subtraction.
Got it.
And so that also works. Now there's another question you might be asking, which is like, what if there's a region of phase space in the data that's not in a simulation? This is like the most nefarious version of the question you could be asking.
Okay.
And
good point.
And yeah, in that case, Omnifold doesn't work. So a core assumption of Omnifold is that the likelihood ratio is everywhere, not infinity. And so that is to say that there's no region of phase space that the simulation doesn't cover. And that's a pretty good approximation because QCD is very generous. Basically anything that can happen will happen. And Pythia basically fills up everything. But you could imagine there's some crazy regions of phase space that like for some reason there's like a dead cone, like QCD says, no, you can't do that. And then like for some reason the data gives you the thing. And then the likelihood ratio this won't work because this assumes that basically you can compute P of X over Q of X.
I see, and Q of X can never go to 0 anywhere effectively. Okay.
Exactly, yeah, and basically in all these examples, it's not a problem because I mean, like I said, QCD is very generous to us. But that is a key assumption, and there are some cases where that just doesn't happen. So.
Okay. All right. No, I think you covered all the questions I didn't know I meant to ask. That's certainly the case. So that gives me a little bit more comfort, I think, on this. Fred, you had a question as well.
Yes, again, yeah, thank you for the presentation. You touched on sort of the computational challenges of this. To do the unweighting, you said you have to pull everything in. And then is that, I mean, once you do that, then you write the data out. At that point, if I want to do an analysis and you give that to me, is that I just do a sequential thing over that, like a data summary? So once you do the unweighting, is that the hard part? And And how well does it scale? I mean, with the large Atlas data sets, is this a challenge?
Right. So there's like the unfolding part, and there's like, what do you do with the result once you have it? And so for both cases, well, let's start with just the unfolding part. With the unfolding part, you have to read into memory your simulated data set and your data set, the one from the collider. And those could both be pretty big. So if you just like take like all the hadrons in the Z plus jet data set from Atlas or CMS run 2, we're talking like many terabytes. And there is no single GPU that exists right now that can load into memory a few terabytes of memory. That's just not possible. And so, and in fact, doing that distributed is also really complicated because the state of the art single GPU is like many tens of gigabytes. And so that's you're talking like very like pretty large number of GPUs for distributed training. So that's a challenge. And so so to begin, you might have that's a challenge we have to solve. Another challenge is like, what do you do with the result? So in the usual way that we present results at the LHC is we have, like I said at the beginning, you have like a vector basically, which represents a histogram. And so if you're like a theorist who's reinterpreting some data, let's say you want to do like, I don't know, a PDF fit, for example, which I understand some of you are really into doing. So in that case, right, you have like a histogram from Atlas or CMS, and you have a vector of values and a vector of weights, like uncertainties, right? And so that's like maybe like definitely like we're talking like kilobytes or smaller, right? Now in this unbinned representation, you basically have all of the simulation data and a weight for every simulated event, right? And so that could easily be terabytes. And so that kind of breaks the workflow because now you have this like huge data set you have to figure out how to parse. Basically, it's just as big as the experimental one, roughly. And there are a couple ways around that. So instead of publishing the simulation events with weights, you could just publish the weighting function because it's a neural network, and the neural network is just a function. So you could like publish the function, which is like we're talking instead like megabytes or smaller, and then like the settings that you use to run Pythia. And like if you did that, like the two of them combined would basically be sufficient to regenerate the data set. But when you're doing your fit, you still need to be able to generate events. So like you still need to probably make histograms or do it unbinned. But that indeed will be a computational challenge that if this is like if this is how we do it in the future, then we'll have to think about how do we do these kind of fits to unbinned data that are not that require a lot of memory to represent.
Okay. Yeah. No. Thank you. That's fascinating.
All right. Well, thank you very much, Ben. I think we've. Oh, sorry, Pavel. You have one more question. We'll end with Pavel. Last question. Okay, Pavel, you're good. Done.
Yeah, well, since you mentioned PDF, so just to understand again, of course, in the PDF case, we have an issue with separating the dependence on the true parameters from what we call the nuisance parameters. And in any experimental analysis, there will be zillions of nuisance parameters, and presumably we cannot simulate the probability distribution with respect to all of them. So again, how will you draw those lines? So what goes into this training of the neural networks versus something that you will treat as this nuisance factors that you somehow do not wish to include in the final analysis?
Right. So the result of the Omnifold will be you have like your simulated event, particle level simulation, and then weights, and then weight uncertainties. And the way it will work is that for every event, you'll basically have a vector. You'll have a nominal weight and then a vector of weights, and all those vectors of weights will be like the nuisance parameters. And as a user, you can kind of decide to like draw a line somewhere and say like if the average weight is below some value, just ignore it. Or the average weight variation, I guess, is below some value, ignore it. And so that is still possible. You can still do that here. What will be more challenging is that now you just have a lot of data, right? And you could, of course, do a processing step where like you say, I'm going to bin everything with my favorite binning scheme and then forget that the data were unbinned. That's one possibility. Mm-hmm. But that's kind of unsatisfying because the data are unbinned. So wouldn't it be better to do your fit in high dimension, in the high dimensional space in its natural unbinned nature? And that will require some more computing power. But I think that more computing power will be possible in the future, and so I think that will be very natural.
Okay, good. Well, thank you so much, and thank you for answering my question. And hopefully, okay, I didn't hold everyone back by it. So, but thanks again for this talk.
Yeah, no, that was great. Thank you, Pavel. And with that, thanks to you, Ben. We really appreciate you taking the time to do this. And I think we'll go ahead and close out the event. Okay, so thank you very much and have a good evening / afternoon, whatever time zone you're in, everybody. All right, bye.
Appreciate it.